My apologies over that. Next up, we would like to integrate this. Sorry, we'd like to integrate 18 minus 5x over, just write it out for you, over x into x minus 3 squared. And we have been told to use partial fractions to integrate. And so what this means is that we're just going to basically make use of, first off, the fact that the integral of f of x plus g of x dx is going to be equal to the integral of f of x over dx plus the integral of g of x dx. Additionally, we'll be using the fact that any fractions, let's say we have 18 over minus 5x over x into x plus 2 as the example. We know that this can be rewritten as a over x plus b over x plus 2. And this is just simply how fractions are added up. And so what we're basically going to do is we currently have this fraction in this form. And so first we want to change it into this form. And then we are going to apply our first one here because of the fact that it's easier to integrate a over x and b over x plus whatever. And so applied to our specific question, we have 18 minus 5x over x into x minus 3 squared. And we know that this can be rewritten as a over x plus b over x minus 3 plus c over x minus 3 squared. And that's just because this is a square term. This one is just the power of 1. And so you need to write it out with all of its exponent terms until you reach the actual number here. So we have 1 and then 2. So next up, we are going to try and find our ABC. And we're just going to do that by doing a into x minus 3 squared into x minus 3 plus b into x minus 3 squared plus c into x minus 3 all over x into x minus 3 into x minus 3 squared. If you want to know how I did that, I just did a multiplied by the other denominators plus b multiplied by the other denominators plus c multiplied by the other denominators too, so that I can multiply them all as my final denominator. And of course, since we want the final form to be x into x minus 3 squared, we're actually going to cancel out this additional x minus 3 here on all of the terms. And so we have one here, one here. We're going to cancel out one here and this one here too. And so what that will leave is a into x minus 3 squared plus b into x minus 3 plus c simply into x all over x into x minus 3 squared. And we know that we want this to give a final value of 18 minus 5x into x multiplied by x minus 3 squared. And so we have the denominator in the correct form. Now we want to expand out this numerator in order to figure out our a, b, and c based off of the coefficients we have here on our x terms. And so let's go ahead and do that. This will become a into x squared minus 6x plus 9. Yep, this will become b into x squared minus 3x, and this is simply c into x over our denominator, and then just put in the terms. So this is ax squared minus 6ax plus 9a plus bx squared minus 3bx plus cx all over what we know And then next up, we want to group our terms. So for the x squareds, we have a plus b into x squared, plus for the x terms, we have negative 6a minus 3b plus c into x. And then lastly, for the x to the power of 0 terms, we're going to have simply 9a. Yep. All over what we have. And as we said, we want this to become 18 minus 5x over what we have. And so we know that this means a plus b must be equal to 0. 9a must be equal to 18. So first let's use these two. 9a is equal to 18 would imply a is equal to 18 over 9. So a is equal to 2. That would change what this means into 2 plus b is equal to 0, which would imply b is equal to negative 2. And then lastly, we have negative 6. We're going to put in our a value, so by 2, minus 3 into negative 2 plus c is equal to negative 5. Let's expand out our terms. This will become negative 12 plus 6 plus c is equal to negative 5. So negative 6 plus c is equal to negative 5. Move over the negative 6 and we get c is equal to negative 5 plus 6, which is going to leave us with 1. Let me just ensure all of those are correct. Yep. And so what all of this means is we're going to put in our ABC back into what we have here. So this, since we found A, B, and C. And so we get 18 minus 5x over x into x minus 3 squared is going to be equal to a over x, so 2 over x, plus b over x minus 3, so that's going to become negative 2 over x minus 3, my apologies, plus c over x minus 3 squared, and so that's 1 over x minus 3 squared, just ensure we've copied the right thing. So a over x, b over x minus 3, c over x minus 3 squared. So we'll just put those values in. And so next up, we're just going to use the first rule here and expand out our fraction. And so that is going to become the integral of 18 minus 5x over x into x minus 3 squared over dx is going to be equal to the integral of 2 over x plus negative 2 over x minus 3 plus 1 over x minus 3 squared. This is all over dx, and then we're going to expand this out. So it'll become the integral of 2 over x dx plus the integral of negative 2 over x minus 3 dx plus the integral of 1 over x minus 3 squared dx. And so we're going to find these individual integrals. For the first one, we're going to pull out the 2 because it's a constant. So the integral of 2 over x would be equal to, over dx, is equal to 2 by the integral of 1 over x over dx. And we know this as equal to 2 ln the magnitude of x. Sorry, just one moment. Yeah. Next up, we have, we're not going to add the plus c right now because we will add it at the end. The integral of negative 2 over x minus 3 over dx. That is going to become negative 2 multiplied by the integral of 1 over x minus 3 dx. Next up, we're going to use substitution and state u as x minus 3, which means du over dx is going to be equal to 1. So du is equal to dx. We're going to plug that all in here, so it becomes 2 into the integral of 1 over u du. Again, we know this as negative 2 into ln of the magnitude of u. And then we just plug in what our u is. So negative 2 ln the magnitude of x minus 3. And then we do our last one, which is the integral of 1 over x minus 3 squared over dx. So again, we're going to set u equal to x minus 3. du over dx is going to give us 1, which implies du is equal to dx, meaning that this integral will become the integral of 1 over u squared dx. And then we're going to use the exponent rule here. We know that the integral of du here. So u to the power of a over du is going to give us 1 over a plus 1 u to the power of a plus 1. And so we're just going to apply this with the situation of a is equal to negative 2. And it'll become 1 over negative 2 plus 1 into u to the power of negative 2 plus 1. And that is going to become 1 over negative 1 u to the power of negative 1. So that's just negative 1 over u. And then we just plug in all of these integrals that we have found now back into this, because we know that these two are going to be equal. So that is going to give us the final answer of the integral of 18 minus 5x over x into x minus 3 squared dx is going to be, so the integral of 2 over x, and we found that that is going to be 2 ln x plus, next up we want the integral of negative 2 over x minus 3. We found that that is negative 2 into the ln of x minus 3. So this will become a negative. And then lastly, we want the integral of 1 over x minus 3 squared. And we have found that to be negative 1 over u. We know that u is x minus 3, so we're just going to plug that in too to become negative 1 over x minus 3. And then we're going to add the plus c because it's an unbounded integral. Sorry, let me just ensure everything is okay here, and it is. And so our final answer is going to become 2 ln x minus 2 ln x minus 3 minus 1 over x minus 3 plus c. And that's our final answer. Okay, for this question, we're going to be making use of our special triangle. So let's just, okay. So we want to find the exact value of the expression, the tan of the inverse cos of negative square root 2 over 2. Square root 2 over 2 we know is a special triangle identity for one of the cosangles. So what we're going to do is find out what that cosangle is so that we can get the value of the inverse cos of negative square root 2 over 2. And then we're going to take the tan of that angle. That angle is going to be a special angle too because we've derived it from an identity that uses the special angles. And so we should be able to find tan of that angle, again, using the special triangles. And so let's begin by sketching them out. Okay, and so we know the typical 45, 45, 1, 1, square root 2. I'm going to use k values instead and radians. So this is pi over 4, pi over 4. If we have k, we would have square root 2 multiplied by k. And then for this one, we have the 30-60 special triangle. So it's going to be pi over 6, pi over 3. And then if we have 1 over 2h by root 3 over 2h, the hypotenuse is going to be h. Okay, and so we're going to use SOHCAHTOA to find all of our angles. Let's start with cos because that's the one that we're really interested in. So if we're looking for the cos of pi over 4, that is going to be adjacent over the hypotenuse, so that is equal to k over root 2k. And this will become 1 over root 2. And then we just multiply it by root 2 over 2, which is 1, so that it can become root 2 over 2. So already we found the angle that we're looking for, but clearly it's not the negative that's inside of the question. And so we need to remember the negative angle formula of cos. First, we know that inverse cos of pi over 4 is going to therefore be, of root 2 over 2 is going to be pi over 4. But then again, let's remember the negative cos formula of cos of pi minus theta is equal to negative cos theta. And so cos of pi minus pi over 4 would give us negative cos of pi over 4, and that will give us our negative square root 2 over 2, because we're just going to multiply square root 2 over 2 by the negative. And so let's figure out what cos of pi minus pi over 4 is going to be. That's going to be 3 pi over 4 is going to be negative root 2 over 2. What that is going to mean is that the inverse cos of negative square root 2 over 2 is going to give us 3 pi over 4. And so we're just going to plug that into what we have, and we're looking for the tan of the inverse cos of negative root 2 over 2. And that is going to be the tan of 3 pi over 4. Okay, and so now we're going to want to go back to the special triangles and use the tan to figure out which, what the answer to this is going to be. Okay, and so if you quickly look at the triangles, we see that none of the angles here are going to be 3 pi over 4. We have pi over 4, pi over 6, and pi over 3. But we can convert this into pi over 4 and see what tan pi over 4 is going to be using a similar rule to the cos one that we used above. And that is going to be the fact that the tan of pi minus theta is going to be equal to the negative tan of theta, which means the tan of pi minus pi over 4, which is equal to the tan of 3 pi over 4, is going to be equal to the negative tan of pi over 4. Pi over 4 is something that we can find here. And so again, back to your special triangles, just remember SOHCAHTOA. So we are looking for the opposite and adjacent. And so we look to our pi over 4 angle, opposite is k, adjacent is k, which means that tan of pi over 4 is going to be k over k, and that is going to give us 1. So the negative tan of pi over 4, which is equal to negative 1, is going to be equal to tan 3 pi over 4. And this is going to be our final answer. So the final answer should be that tan of the inverse cos of negative root 2 over 2 is going to give us negative 1. Okay, for this one, it's just pretty basic integrals. So for our first one, we are going to use x to the power of 10 dx. We're going to be using the integral rule for exponents, and that just states that the integral of x to the power of a over dx is equal to 1 over a plus 1 x to the power of a plus 1 plus c if it's unbounded. And so now we just apply that to our situation where a is equal to 10, and that would become the integral of x to the power of 10 dx is equal to 1 over 10 plus 1, that's going to be 11, x to the power of 10 plus 1, which is also going to be 11, plus c. And that's going to be our final answer. Next up, we have the integral of 8x to the power of 6 over dx. First off, we're going to simplify this integral, and we're going to use the fact that the integral of a constant a multiplied by a function of x all over dx is going to be the same thing as if you pull out that constant and do the integral. So what that means is that we can pull out that 8, so it becomes the integral of 8 by x to the power of 6 over dx is equal to 8 multiplied by x to the power of 6 dx. And then next up, we're going to use the exponent rule like we did in the previous question, where we know that the integral of x to the power of a over dx is 1 over a plus 1 x to the power of a plus 1 plus c. So what that means for our question is that the 8 multiplied by the integral of x to the power of 6 dx is going to be 8 into 1 over a plus 1, 9, x to the power of a plus 1, so that's 9 plus c. Multiplying 8 by the constant, it's still going to be a constant, so we can just label that new constant c2. You can name it something else, but we've been told specifically to use c for the constant of integration, so our answer will become 8 over 9 x to the power of 9 plus c. And that's going to be our final answer for this one. Lastly, we are going to be integrating 3 to the power of 4 plus x to the power of 13. This is all over dx. So we are going to use the additive property that the integral of f of x plus g of x over dx is equal to the integral of f of x over dx plus the integral of g of x over dx. So applied to our question, that means that the integral of 3 to the power of 4 plus x to the power of 13 all over dx is going to be equal to the integral of 3 to the power of 4 dx plus the integral of x to the power of 13 dx. So we need to evaluate these individual integrals. First up, we are going to use the constant one that we just previously talked about. Is equal to, pull out the constant, f of x dx, to this one. So that will mean that the integral of 3 to the power of 4 dx is equal to 3 to the power of 4 multiplied by the integral of dx. We know that the integral of 1 multiplied by dx is simply x, so that will become 3 to the power of 4 multiplied by x. And then for this one, we're going to use the exponent rule as we have in the previous ones. So that will become that the integral of x to the power of a dx is 1 over a plus 1 x to the power of a plus 1 plus c. We're not going to write down the plus c, we'll write it down at the end because it'll always just remain a constant whether you multiply it by another constant or not. And so it'll become 1 over 13 plus 1, so 14, multiplied by x to the power of 14. Is equal to the integral of x to the power of 13 dx. And so that means that the integral of 3 to the power of 4 plus x to the power of 13 dx is going to be equal to this, which we have found is 3 to the power of 4 multiplied by x plus the integral of x to the power of 13, which we found here. And then lastly, the plus c, because it's an unbounded integral. You can write out the 3 to the power of 4 at the end if you'd like, or leave it like that. Okay, next up we're looking for the Taylor series. For the ln of 1 plus x. So in order to find it, we need to remember the Taylor series formula, which is just the summation from n is equal to 0 to infinity of the function. You take the derivative to n, evaluated at a, over n factorial multiplied by x minus a to the power of n. Okay, and so we know that f of x, let's start by finding, sorry about that, ln u. So the Taylor series for ln of x, and then or ln of u, and then you just plug in the u as 1 plus x in your formula that you've derived, and then that would be your final answer. And so it's evaluated at ln x. So f of x is equal to ln x. We know that the first derivative is going to be equal to 1 over 1 plus x. The second derivative is going to be negative 1 over 1 plus x squared. The third derivative is going to be 2 over 1 plus x cubed. The fourth derivative is going to be equal to negative 6 over x plus 1 to the power of 4. And so let's go ahead and write out our summation. So it'll become so that would look like that, evaluated at a over 0 factorial, negative a, x minus 0 to the power of 0 plus the first derivative, evaluated at a over 1 factorial, x minus 1 to the power of 1, and you just go on like that, adding up the n values. And so we're just going to go until the fourth n value because we have the derivative until that number. You can keep going, but you can develop a sense of the pattern if you just have a few of them. And so if you put in what we have, it'll become the 0th derivative, and so that's just going to be ln, evaluated at a, x minus 0 to the power of 0 is 1, 0 factorial is 1, so that will be left like that. The first derivative is 1 over 1 plus x, but remember it's evaluated at a, so the x will become 1 over 1 plus a over 1 factorial, so that's just going to be 1 over 1. Multiplied by x minus 1 to the power of 1. Next up, we have the second derivative. So that is negative 1, evaluated at a, over 1 plus a squared into x minus 2 squared, plus, so 0, 1, 2, the third derivative. So 2 over 1 plus a, let's not forget about the factorial. So it's supposed to be over 2 factorial. 1 plus a cubed. Into x minus 3 cubed plus, and just keep going like that. We can include the fourth one if we'd like. So this would become minus 6 over 1 plus a to the power of 4 multiplied by x minus 4 to the power of 4 over 4 factorial. And so now we'd like to look at what we have here and try and see if we can see a pattern that we can just again represent with a summation. And the pattern that you actually pick up would be, let's first take out this ln of a. And then let's have the rest of the terms. And with the rest of the terms, you can actually begin to see a pattern if we start at n to the power of 1. Sorry, n is equal to 1. So it'll become ln a plus the summation from n is equal to 1 to infinity of -1 to the power of n plus 1. So the -1 there is because of the alternating pattern in the sign. So positive, negative. This way, when you start at 1, this would be -1 squared, so positive, and then it'll become -1 to the power of 3, so negative, and so on and so forth. And then we have over n multiplied by x minus a over a plus 1 all to the power of n. And so the reasoning for it being just over n and not factorial is because 3 factorial is going to be 3 by 2. The 2 will cancel out with this one in the numerator. 4 factorial is going to be 4 by 3 by 2. The 3 by 2 is going to cancel out with this 6, and so on and so forth. So it'll cancel out the fact that it's factorial because of these coefficients that we have here. And so this is going to be your final answer for ln of x. Right? And so that means that the ln of x plus 1 is going to be the ln of a plus 1 plus the summation from n is equal to 1 to infinity of -1 to the power of n plus 1 over n. And then we're going to put in x plus 1 as our x minus a over a plus 1. Sorry, this is going to remain ln of a because it doesn't have an x value in it. And then this is all to the power of n, as we see here, which means that the ln of x plus 1 is going to be ln a plus the summation from n is equal to 1 to infinity. The -1 remains the same over n. X plus 1 minus a is just going to stay x plus 1 minus a because we can't simplify it further. In the scenario where you can, and like it's x plus x squared, then we can simplify that. But in this case, we can't. So we just leave it like that. And that's going to be your final answer. Next up, we want to evaluate this integral, e to the power of -2x sine 2x over dx, and we're going to be using integration by parts. So to figure out what our u is going to be between inverse, trig, logarithmic, algebraic, trig, and exponential, which one do we see? And so we see the trig before exponential, which means our u is going to be equal to sine 2x, and our dv is going to be equal to e to the power of -2x. This means that v is going to be equal to -e to the power of -2x over 2. And this means that the derivative of u, so du, is going to be equal to 2 cos 2x dx. And so now we're just going to use the formula we know for integration by parts. So the integral of u dv is equal to uv minus the integral of v du. Let's go ahead and plug in our values. The integral of e to the power of -2x sine 2x dx is equal to sine 2x multiplied by negative e to the negative 2x over 2 minus the integral of negative e to the negative 2x over 2 into 2 cos 2x dx. Okay, and so now that we have this, we see that this is another integral that we're going to have to figure out. And so let's go about finding all of this in a form where we don't have any integral, so we can just state that this is equal to this, basically. And so we will have that if we set u as 2 cos 2x, I decided that based on the algorithm that I listed above. That means that dv is equal to negative e to the power of negative 2x over 2 dx. This means that du is going to be equal to negative 4 sine 2x. And this is du. V is going to be equal to negative e to the power of negative 2x. Sorry, not negative, positive over 4. Yeah. And so let's just plug in those into the same formula we have up here, and we have the integral of negative e to the negative 2x over 2 cos 2x dx is going to be equal to uv, so 2 cos 2x multiplied by e to the negative 2x over 4 minus v du, so the integral of e to the negative 2x over 4 into du, so negative 4 sine 2 x dx, right? And so what we are going to do is simplify this a little bit. So the negative here is going to cancel out this negative, and this 4 is going to cancel out this 4. And so this will become 2 cos 2x over 4. Sorry, those two will cancel out 2. Becoming cos 2x multiplied by e to the negative 2x over 2 plus the integral of e to the negative 2x sine 2x dx. And so now we're just going to plug all of that right back into here. And so we will get that the integral of e to the negative 2x sine 2x dx is equal to negative sine 2x e to the negative 2x over 2 minus what we found as the integral here. So it's minus cos 2x into e to the negative 2x over 2 minus the integral of e to the negative 2x sine 2x dx. Now what happened here is that we have this is the exact same thing as this. So we're going to move it over to the other side. So that it becomes 2 multiplied by the integral of what we're looking for is going to be equal to, we can pull out the negative 1 over 2, and then the e to the power of negative 2x too. And we'll just be left with sine 2x plus cos 2x. And so now we're just going to isolate for what we're looking for. So e to the negative 2x sine 2x dx, the integral of that is going to be negative 1 over 4 e to the negative 2x into sine 2x plus cos 2x plus c, because the integral is unbounded, and that's going to be your final answer. So we want to determine a power series centered at 0 for the function, and so let's go about doing that. And we're given the power series that 1 over 1 plus x is equal to the summation from n is equal to 0 of negative 1 to the power of n multiplied by x to the power of n. And so that means that when we have 1 over 1 plus 16 squared, what we're going to do instead, you can decide to rewrite this as 1 plus 1 plus 4x squared. It's basically the same thing. What we're going to do is we're going to put in this 4x squared in the place of x in this summation. So it's going to become the summation from n is equal to 0 to infinity of negative 1 to the power of n multiplied by 4x squared all to the power of n. And so you're going to end up distributing the square term and still ending up with 16 squared. That's why it doesn't matter which form you decide to present it in. And so that just becomes the sum from n is equal to 0 to infinity of negative 1 to the power of n, 16x squared to the power of n. And that is the summation from n is equal to 0 to infinity of negative 1 to the power of n, 16 to the power of n, and x to the power of 2n. And that is going to be the final answer for the summation. Next up, we need to find out the integral of convergence, and we're going to do that using the ratio test. And so we know that the ratio test states that the summation will converge so long as the magnitude of L is less than 1, and L is equal to the limit as n approaches infinity of what we have inside the integral with n plus 1 instead of n over un. And so what that is going to be is the limit as n approaches infinity of, let's state un plus 1, so that is negative 1 to the power of n plus 1, 16 to the power of n plus 1, x to the power of 2n plus 2. And that is all going to be over the same thing, but with n. So negative 1 to the power of n, 16 to the power of n, x to the power of 2n. And then we're going to simplify what's inside. And it'll become negative 1, just using exponent rules. So negative 1 to the power of n plus 1 minus the n in the denominator into 16 to the power of n plus 1 again minus the n in the denominator, and x to the power of 2n plus 2 minus the 2n in the denominator here. And so that becomes the limit as n approaches infinity of negative 1 to the power of 1, 16 to the power of 1, and that's the x to the power of 2. Notice none of these terms contain n, and so as n goes to infinity, it has no effect on the value of what's inside of the absolute value. And so this will just become, the magnitude of negative 1 is going to be 1. So 1 by the magnitude of 16 is 16 multiplied by the magnitude of x squared, and that's just going to be x squared. And so L is going to be 16x squared. And we're given the identity that the summation is going to converge as long as the magnitude of L is less than 1. We're just going to put in what our L is. So 16x squared is less than 1. And then we know that we can pull out the 16. X squared is less than 1. And we can additionally pull out the square root because x squared is equal to x by x. which can be written as the magnitude of x by the magnitude of x, and that is the magnitude of x squared. And so that will become 16 into the magnitude of x squared is less than 1. We move over the 16, 1 over 16, and so we're given as long as the magnitude of x is less than the square root of 1 over 16. So that is going to give us the inequality that x is going to be between negative 1 over 4 and 1 over 4. And that's dictated by this relation we got from the ratio test. And those are your final answers. Okay, for this question, we're answering what an iterated integral is. And so there is the actual definition is linked below the question on OneClass. But if you're given this and you just genuinely did not know the answer, we can just look at the words in it, quite literally. Iterated reminds you of the word iterations. And we've seen this word in math a lot. Iterations means you're repeating whatever it is you did. And so if we're doing iterations of derivatives, that means you're repeating taking the derivative multiple times. So you take the derivative the first time, and then you take the second derivative, and then the third derivative. And let's say you decided to stop here, you would say the third iteration of the derivative. And so now that we're talking about integrals, iteration reminds you of doing something multiple times, right? So now that we're talking about integrals, that means that we're going to be integrating multiple times, is what the question basically tells you straight up. And so in integrals, what is going to cause us to integrate multiple times would be the presence of multiple variables in whatever our function is. So these are called multivariable functions, and they can spit out scalar values or other vectors. And so if we have f of xy or f of xyz, you could have as many variables as you'd like, or as given in the question. So let's take the example of f of xy. What integrating multiple times would look like would be integrating over x, and then integrating over y, fx, y, and let's say we're doing dy, dx. And so this would be a double integral. And so this gives you a more intuitive feel, I guess, on what the words actually mean before you get into the definitions. The definition online is it's an integral formed upon integrating a function of more than one variable in a way that each of the integrals considers some of the variables as given constraints. And so what I've described here basically. And so first we'd integrate over y, whatever the function is, and as we're integrating over y, we're going to treat the x values inside of this function as though they're just constants, because we currently don't care about them because we're integrating over y. And then after we get the answer for the integral of f of xy, we're going to integrate over x next. And since we've already taken the integral with respect to y, there'd be no more y terms left, only x terms or constants, and then you get your final answer. And so a good example of this would be, let's say we have the function f of xy is equal to xy as an example, right? And then we'd like to integrate last as x goes from, so x is equal to 1 to x is equal to 3. But firstly, we'll be integrating from y is equal to 2 to y is equal to 6, okay? And so since we have xy dx dy, right? And so first, you're going to treat the x term as a constant. So if it was a constant, we know that the integral of a into f of x times dx, we can pull out that constant. And so that's exactly what we're going to do here. And we're going to pull it out. So it becomes the integral from x is equal to 1 to x is equal to 3 of x, multiplied by the integral from y is equal to 2 to y is equal to 6 of y dy dx. My apologies, you're supposed to say dy first because it's the first integral that you're taking, and then the dx. Okay, and so we know that the integral of y, just using exponent rules, is going to be y squared over 2. And we're taking it from y is equal to 2 to y is equal to 6. This is still within integration bounds, but let's first evaluate this. So we come from x is equal to 1 to 3 of 6 squared over 2 minus 2 squared over 2 dx. So 1 to 3 of 36 over 2, which is 18, minus 2 squared over 2, so 4 over 2, and that is going to give me 2 over dx. So 1, 2, 3 of, don't forget the x term that was here, my apologies, of x into 18 minus 2, which is going to be 16. And so now we're going to figure out this integral next. So it becomes from 1 to 3, we're going to pull out the 16 because it's just a constant. So 16, 1 to 3 of x dx, which will become 16 into x squared over 2. 1, 2, 3. So 16 into 3 squared, so 9 over 2 minus 1 squared, 1 over 2. So 16 into 8 over 2. And this will become 8 by 8. And so that will become, that will become 8 by 8, which should give us 64. And that will be your final answer for the integral from 1 to 3, 2 to 6 of x, y, dy, dx. So this is just an example of how to do it. For our next question, we'd like to prove whether this is true or false. Is the antiderivative of cos x squared sine x squared plus c. And so to begin doing this, we're going to need to find the antiderivative of cos x squared. So we're going to integrate cos x squared without bounds over dx. This is actually, the way that we do this is going to be different from the ways that you know how to integrate other functions, because we're not going to integrate by parts or by substitution. We're going to make this into another integral that actually has an integral identity, and that way we just have the integral identity in our answer. And so we have the integral of cos x squared. We are going to state that u is equal to root 2 over root pi of x. And so du over dx is just going to give us root 2 over root pi. And u squared is going to be 2 over pi x squared. And so for our x squared is going to be pi over 2u squared. And so what that means is that we are going to be taking, here we're going to isolate dx is equal to root pi over root 2 du. So we're going to substitute our x squared in terms of u and our dx in terms of du. And so it will become the integral of cos pi over 2u squared into dx, which is root pi over root 2 du. And this is actually going to become, once you pull out the root pi over 2, root pi over root 2, the integral of cos pi over 2u squared over du. Okay, and then this is actually called a special integral, called the Fresnel integral. And that basically just states that so cx would be defined as the integral from 0 to x of cos t squared integrated over dt. And so that means that this integral that we have, so the integral of cos pi over 2u squared over du is going to be equal to c of root 2 over root pi x would be the value of this integral. And so we're just going to plug that in here to get that the integral of cos x squared dx is equal to root pi over root 2 into c, which is the Fresnel integral, multiplied by root 2 over root pi x, and then we're going to have our plus c at the end. Obviously, this is not equal to sine x squared. Sine x squared actually has its own Fresnel integral, which is sx is equal to the integral from 0 to x of sine t squared dt. What this all means is that the question that we're trying to prove is false. Sorry about that. Next up, we are looking for this integral. And we're going to do it using substitution. So the integral of sec squared x over tan x dx. In this case, we're lucky because we have it in the form f prime of x over f of x dx, which means that if we state that u is equal to tan of x, and we know that the derivative of tan of x is equal to secant squared x dx, that means when we substitute everything back into here, the derivative value would actually cancel out, leaving us with 1 over f of x, or 1 over u du, and that's simply ln of u. And so let's do that. We'd get the integral of secant squared x over u into d of x is equal to du secant squared x according to this. And so we put that in, and these two cancel, as I said, and so it becomes the integral of 1 over u du we know that this is going to give us the ln of the magnitude of u plus c, and then we just put in the u that we have, and we would get ln the magnitude of tan of x plus c, and that's going to be our final answer. Verify the derivative of cotangent and cosecant using the quotient rule. And so they've clearly told us that we need to use a specific rule, so let's just write it down so we can figure out how it applies to our questions. And the quotient rule just states that the derivative of f of x over g of x is going to be equal to g of x multiplied by the derivative of f of x minus f of x multiplied by the derivative of g of x all over g of x squared. And so if we're looking for the derivative of cotangent x, we know that that is equal to the derivative of 1 over tan x, because that is what cotangent is equal to. And we can actually write this further as cos x over sine x, and that's because tan x is sine x over cos x, so just invert that to become cos x over sine x. And so what that is going to mean is f of x is going to be cos x, so the derivative is going to be negative sine x, and lastly g of x is going to be sine x, so the derivative is equal to cos x. And so we're just going to put all of this back into the formula that we have here, and we will get that the derivative of cotangent x is going to be g of x, so sine x multiplied by negative sine x minus f of x, so cos x, into the derivative of g of x, so that's cos x too. This is all over g of x squared, so sine x squared. If we write that out, that is negative sine squared x minus cos squared x all over sine squared x. Okay, and we have an identity that states that sine squared x plus cos squared x is equal to 1. And we can see that we can get this numerator into that form if we have negative sine squared x plus cos squared x all over sine squared x. And so this is going to become 1 according to that identity. So we have negative 1 over sine squared x. And lastly, we know that 1 over sine x is cosecant. So this would become negative cosecant squared x. So the first one is proven. Let's move on to the next one. We are looking for the derivative of cosecant x. And we know that cosecant x, as I just stated, is 1 over sine x. And we can apply the quotient rule to this, where we have f of x is equal to 1. The derivative of f of x is going to be 0. G of x is equal to sine x, and the derivative of g of x is going to be equal to cos x. And so what this is going to become is d over dx of cosecant x is going to be sine x multiplied by 0 minus 1 multiplied by cos x all over sine squared x. So this will become negative cos x over sine squared x. And we know that this can be rewritten in the form negative cos x multiplied by, over sine x, multiplied by 1 over sine x. We've already established that this is going to be cotangent of x, and this is going to be cosecant of x, and then there's a negative. So all of that means that the derivative of cosecant x is equal to the negative cotangent x multiplied by cosecant x. So we've proven what is in the question, and that is going to be everything for this one. Okay, next up, we're going to prove the derivatives of the hyperbolic functions. And so first up, we have the hyperbolic function for cos. And what that is going to be is e to the power of x plus e to the power of minus x. Let me just make sure I got that right. Over 2. So first, we'll be using a couple of the derivative rules. So we know that d over dx of a multiplied by f of x is the same thing as a multiplied by simply the derivative of f of x, because the constant a has no effect. And so we're going to use that to pull out the 1 over 2. That's how we're going to deal with that. And then lastly, the derivative of f of x plus g of x is equal to the derivative if you took them separately. And so, how we're going to apply this to this is to separate the e to the power of x and the e to the power of negative x, and those are two derivatives that we can easily find instead. And so this means that d over dx of e to the x plus e to the minus x over 2 is going to be equal to 1 over 2 into the derivative of e to the x plus e to the minus x, and then we're going to separate them into d over dx e to the x plus the derivative of e to the minus x. And then next up, we're going to apply this derivative. Is quite easy to find. We know the derivative of e to the x is e to the x. And this one, we're going to use a chain rule to make it as easy to find as the other one, where we know dy over dx is equal to dy over du into du over dx. So if u is equal to negative x, then that means the derivative of e to the power of u over x is going to be dy over du, so that's e to the u, multiplied by the derivative of this with respect to x, and that's just going to be negative 1. So it becomes negative e, and then you're just going to put in the u, so to the negative x. And so what this will now become is that the derivative of this is equal to 1 over 2 into e to the x minus e to the minus x. And if we rewrite all of that, that becomes e to the x minus e to the minus x over 2. And this is also another hyperbolic function of sine. And that's your final answer for that one. Next up, we are looking for d over dx of the hyperbolic function for tan. And we know that this is equal to the hyperbolic function of sine over the hyperbolic function of cos. So what we're going to do here is we're going to use the quotient rule. So let's just quickly write down what that is. Okay, and so in our question, we have that f of x is equal to that, and g of x is equal to this. We already determined the derivative of this, and that is going to be that. And in similar fashion, if you go through the same process, but instead with the hyperbolic function for sine, you are going to get that the derivative is actually the hyperbolic function for cos. And so now when we plug all of that into our formula here, it will become into minus into, and this is all going to be over that. And so this will become squared plus, sorry, this is minus. And we actually have an identity here too, where we know that sorry, just one moment. Here it is. Is equal to 1, and so we're just going to put that in here, and it will become 1 over that, and this is actually equal to that, similar to how secant is 1 over cos. So the hyperbolic function for secant is 1 over the hyperbolic function for cos, and that is going to be our final answer for that one. Next up, we are looking for this. So as I said, that this is equal to 1 over the hyperbolic function for cos. And so again, we're going to apply the quotient rule. We have f of x is equal to 1. The derivative is going to be equal to 0. G of x is equal to the hyperbolic function for cos of x. And we found that the derivative of that is, of course, the hyperbolic function for sine of x. And so we're just going to plug that all into our formula for the quotient rule, and that will become 0 into that minus 1 into that. And that is all going to be over this squared. So that'll become negative . And this can be rewritten in a form that is a bit more familiar to us. And of course, this is equal to the negative hyperbolic function for tan multiplied by the hyperbolic function for secant. And that's going to be our final answer for that one. I had skipped the question right before that, so let's go ahead and cover that. So we know that this is going to be 1 over that. And so again, we're going to use the quotient rule. And as we said before, the derivative of this is going to be equal to the hyperbolic function for cos. So we're just going to plug that all into the rule that we wrote before, so that it can become 0 into that minus 1 into that all over this squared, and that will become negative hyperbolic cos over hyperbolic sine squared. We can again rewrite that into a form that's more familiar. And this will become negative the hyperbolic for the cotangent multiplied by the hyperbolic for secant. And that will be your final answer. Let's draw a last one. So this will become the inverse of the hyperbolic function for tan, and so that's going to become cos hx over sine hx, and then we are going to treat f of x as the inverse for cos, which means that the derivative of x is going to be the inverse for sine. Similarly, g of x is going to be the inverse for sine, and the derivative will be the inverse for cos. And then we just plug in all of those values and we get minus over, and so this will become this. And then let's see if we have any identity for that. Okay, so we know that this can be rewritten in the form negative minus this. And we use this identity in the first question. We know that this is going to be equal to 1. And so we'll get negative 1 over that, and that will be negative cosecant squared of x. Sorry, hyperbolic cosecant. And that's going to be our final answer. Okay, lastly, we have this question. There are two ways to do it, using Lagrangian multipliers or using, or alternatively using a different method. And so first, let's use the one given to us here. We have a rectangle with a square base, so we can draw it like that. Square base means that we have x by x, and then we have it being with a height of h. So what that means is that the surface area is going to be 2 by x squared, because we have those two faces, plus 4 multiplied by xh is going to be our surface area. Our volume is going to be simply x squared multiplied by h. And so we're given that we don't know, we're trying to find the surface area, so we can leave it like that. And then we have the volume as x squared h is going to be equal to 8,000. And so what we're going to do is we're going to isolate for h, and we get h is equal to 8,000 over x squared. We're going to plug this back into the surface area, and we get 2x squared plus 4x into 8,000 over x squared. And that is going to become 2x squared plus 4 into 8,000 over x. And so to find the extrema of this, so the minima is what we're trying to find, we're going to take the derivative to find the extreme points. So we can get 4x plus minus, sorry, because of the 1 over x. So minus 3,000 over x squared. And then we're going to set this equal to 0 and solve for x. And so we get 4x is equal to x squared over that. And then we are going to cancel our x terms to get 4 is equal to x over this. Sorry, my apologies. Yeah. And this will lead us to the conclusion that x is equal to 20. Yeah. And then lastly, we know that h is going to be equal to 8,000 over x squared. And so you're going to just put that in. And that will give you h is going to be also 20 inches. So in order to minimize the surface area and keep the volume at what is given in the question, you will have a height of 20 inches and a length of 20 inches too. So you'll have a cube basically. There is a different method to do this, as I had said, using Lagrangian multipliers, and we can just state that as is equal to that. G is what is going to be your limitation, and F is what you're looking for. So in this scenario, our F is going to be equal to the surface area, and it is going to be 2x squared plus 4xh. And our G is going to be equal to the volume, and it will be x squared h. What this means is that we're going to have in vector form the derivative with respect to x followed by h. So let's just write that out. That becomes 4x plus 4h. And then the derivative with respect to h is going to become 4x. And should be equal to derivative with respect to x first, so 2xh, derivative with respect to h, so x squared. What this means is 4x plus 4h is equal to that into 2xh, and 4x is equal to that into x squared. How we're going to solve for this is we want to find mu xh such that the volume statement, so our g remains correct and our f also holds. And so we can do that by isolating for x here. To get 4 is equal to this by x, which means x is equal to 4 over that. Sorry, alternatively we can isolate for our multiplier. So this is equal to 4 over x. And then you're going to plug that into what you have up here. So you can get 4x plus 4h is equal to 2xh multiplied by 4 over x. That will mean 4x plus 4h is equal to 8h. Bring this over and we get 4x is equal to 8h minus 4h. And so you get 4x is equal to 4h, hence h is equal to x. And so this is what we got using the other method. X was equal to h. To find our actual values, we're going to plug in this equality into our g. And our g was the fact that v is equal to x squared h. This is equal to g of x and h. And so we're just going to plug in x is equal to h. This will become x squared multiplied by x, and that is x cubed. And so we get x cubed is equal to 8,000. And then you take the cube root on both sides. So x is equal to 20, and we know x is equal to h, so h is equal to 20. And those are your final answers. Those are all of... those are all of the questions that I have for you today. I hope you enjoyed today's Q&A. This has been Marlyn from OneClass, and I hope